AI is just everywhere, right? It feels like it's moving at this incredible speed, almost like magic. One minute, it's some niche research project, and the next, it's writing code, making art, and totally changing how we work. So you have to wonder, how on earth did we get here so fast? Well, it's not a story of magic. It's a story of ideas built one step and one research paper at a time.
So to really understand this whole revolution, we're going to use a map. And this isn't just any map. It's a list of 30 research papers curated by Ilya Sutskever, who's one of the key minds behind modern AI. He basically said, if you can wrap your head around these papers, you'll get 90% of what's driving AI right now. So let's use his list as our guide to the big ideas that are building our future.
Okay, let's dive right in. We're about to go on a journey through the fundamental problems that AI researchers had to solve, and the absolute game-changing breakthroughs they discovered along the way. You'll see how one idea just stacked on top of another, leading us straight to the crazy powerful models we have today. You know, before an AI could write an essay or generate a piece of code, it had to figure out two things that we humans do without even thinking: how to see the world and how to understand things that happen in a certain order. That meant researchers first had to conquer images and sequences.
The big key that unlocked computer vision was the convolutional neural network, or CNN. The easiest way to think about it is like a detective scanning a photo for clues. It doesn't just stare at the whole thing at once. Nope, it uses these little filters to find simple patterns first, things like edges or corners. Then, the next layer combines those to find slightly more complex things, like textures and shapes, until, layer by layer, it can finally recognize a whole object, like a cat or a car.
Now, what you're seeing here is basically the one-two punch that started the AI explosion. Back in 2012, AlexNet was the big aha moment. It proved that a really deep CNN could just completely dominate a huge image recognition contest. That was the spark. But then in 2015, ResNet came along and gave everyone the blueprint. See, before ResNet, if you made a network too deep, it actually got dumber. ResNet introduced this brilliant little trick called a residual block that let researchers build these absolutely massive networks. We're talking over 100 layers deep that just kept getting smarter. We went from small buildings to building skyscrapers of intelligence.
Okay, so machines could see. That's a huge step. But what about understanding things that unfold over time? Like the sentence I'm saying right now, or the words on a page. This is the challenge of sequential data, and it needed a totally different way of thinking.
The first really ingenious solution was the Recurrent Neural Network, or RNN. Unlike a CNN, which just looks at a static picture, an RNN has a loop, and this loop gives it a kind of internal memory of everything it's seen so far in a sequence. So as it reads a sentence, word by word, its memory keeps updating, giving it context from what came before. Later versions like LSTMs, or even fancier, giving the memory little gates to help it remember the important stuff and forget the junk.
But there was a big problem. RNNs had pretty bad short-term memory. They were great at remembering the last few words, but in a long paragraph, they'd completely forget what the first sentence was about by the time they got to the end. This issue, this struggle with long-term dependencies, was a huge roadblock. Progress was kind of stuck.
And that brings us to the real turning point of this whole story. Everything we've talked about so far, all the breakthroughs and all the roadblocks, it was all just setting the stage for one of the most important ideas in the history of AI, a moment that was about to change the entire game.
Then, in 2017, a group of researchers at Google published a paper, and it had this deceptively simple title, "Attention is all you need." And it turns out they were absolutely right.
This paper introduced the world to the transformer. Now, you got to understand, this wasn't just a slightly better RNN. This was a completely different way of doing things. It basically took the old rulebook, the step-by-step processing of RNNs, and threw it out the window. It replaced it with something way more powerful called self-attention.
So what in the world is self-attention? Well, think about how you read a sentence. As you look at each word, your brain is subconsciously linking it to other important words to get the full meaning. Self-attention lets an AI do exactly that. For any given word, it can look at all the other words in the sentence at the exact same time, no matter how far apart they are, and figure out which ones are most important to understand its context. It's like giving the AI a superpower to highlight all the relevant connections instantly.
And this new way of doing things had two huge advantages. First, it completely solved that long-term memory problem because it could see everything at once. But second, and this is maybe even more important, the whole process could be done in parallel. That meant we could train these models on gigantic amounts of data way, way faster than ever before. The result? It completely shattered all the old records in things like machine translation, and it became the foundation for pretty much every modern large language model out there.
So, now the world had the transformer architecture. The next chapter in the AI story became all about one thing: scale. What happens if you take this incredible model and just make it bigger, and feed it more data than anyone had ever even dreamed of? Researchers stumbled upon something amazing, which they called the scaling laws. They found that making a language model better wasn't just random guesswork. Its performance actually improved in a very predictable way when you cranked up 3 specific dials: the size of the model, the size of the data set, and the amount of raw computing power you threw at it.
This chart basically lays out the simple brute force recipe for modern AI. You want a smarter model? You need more parameters, you need more data, and you need more compute. That's it. Following this recipe is exactly what led to the mind-blowing jump in abilities we've seen with models like GPT. It turned AI from a quirky science into a predictable engineering problem where bigger was, literally, better.
Okay, so now we have these gigantic, powerful models. But they have one major weakness. Their knowledge is frozen in time. They're like a brilliant historian who knows everything up to the year 2021 but has no idea what happened yesterday. So, how do you fix that? The solution is this really elegant idea called Retrieval Augmented Generation, or RAG. The best way to think about it is like giving the AI an open book exam. When you ask it a question, it doesn't just rely on its own memory. First, a little retriever module goes and searches a massive, up-to-date knowledge base, like, say, the internet, for relevant info. Then it hands that info over to the language model as extra context so it can generate an answer that's not just smart, but also fact-based and current.
So, all these breakthroughs, from seeing pictures to understanding language to pulling in real-time knowledge, that's what's brought us to where we are today. But you have to ask, where is this all heading? What's the ultimate goal that's driving all this research?
The models we have right now are absolutely incredible masters of language and patterns. They can synthesize all the knowledge they were trained on. But for a lot of researchers, the end game is something called machine superintelligence, a theoretical AI that would be smarter than even the most brilliant human minds. That's the North Star that guides a lot of this foundational work.
And that brings us to one last really deep idea that comes from information theory. It's called the minimum description length principle. And what it suggests is that, at its very core, intelligence is all about compression. The best, most intelligent understanding of something is the one that can explain it in the simplest, most compact way possible. In a way, learning is really just the search for that perfect, compressed model of the world. So there you have it, from CNNs learning to see, to transformers learning to pay attention, to models that scale with predictable power. These are the big ideas that built the AI we have today. When you trace their history, you see it's not magic, it's just a chain of brilliant insights. Which leaves us with the only question that really matters. What are the next ideas in that chain? And what are they going to build?